All right. So, taking 2 and doubling it, getting 4, taking that and doubling, getting 8, taking that and doubling, get it 16, double that and get 32, double that, get 64, double that, get 128, and keep going. That is referred to as exponential growth, and that's what we're going to try to investigate here in the next couple of weeks. If you have a great application of the use of exponentials is, you guys ever heard of radioactive decay? Yeah. You guys in science? You doing that in rock class? No. Okay. So radioactive decay is the same thing. Instead of growth, though, it's decay, or kind of like dying. But if I have, so radioactive decay, the way it works, like if I have like carbon-14, let's say I have 100 milligrams of carbon-14. It takes like close to 6,000 years for carbon-14 to go through what we call a half-life, which basically means if I have 100 grams, it's going to take 6,000 years for it to turn to decay and turn into 50 grams. Does that make sense? Okay. And then it'll take another 6,000 years to take that 50 down to 25. And then another 6,000 years to take that 25 down to 12 and a half. And then we keep doing this, so 6.75, and keep going all the way down. I keep cutting it in half. Okay, will I ever have zero carbon-14? No. If you think about this, think about taking like a sandwich. Theoretically, if I took a sandwich and I cut it in half, okay, and then take that half and cut it in half, and take that half and cut it in half, and take that new half and cut it in half, I should be able to do that infinitely many times forever. Does that make sense? Okay. And I should always be left with a sandwich. Okay. Now, the idea with radioactive decay and carbon-14, so they use carbon-14 for carbon dating, right? We know how long it takes for it to go from an initial amount to half that amount. So what we can do is we can reverse the procedure and say, okay, if we have this amount now, if we double it and then double it again, we can start saying, okay, well, this object maybe 12,000 years ago had this much carbon in it, so we can date this object based off that. Does that make sense? You've heard of carbon dating, right? Where you guys know what carbon is, right? Yeah. Okay. So they take the amount of carbon that is in whatever. So maybe it's a piece of cloth, or maybe it's a piece of skin or something like that, and they will do this carbon dating on it, and it will give them a pretty good estimate of how old that artifact is. Okay. Exponential functions allow us to do that. Let's say that something we have just experienced or are currently experiencing as this year has been kind of a mess. We're almost reaching the anniversary of when we had to be sent home, right? Let's say that we have one person infected with a virus. Okay? Let's say that one person gets on an airplane. That's my airplane. Let's say that one person gets on that airplane. Okay? You guys ever been on like a 747? Never been on a plane? Okay. Do you have any idea of how many people are on a plane? Yeah, let's say 200 people. Okay, approximately 200 people. Okay. Let's say that one person. So there, if you've ever been in like a 747, like you're jam packed in there. Okay. You don't have a whole lot of room, so it's a confined space. Okay. Let's say this flight was between like Detroit and Italy. Now let's go Milan, Italy. It's like a 13-hour trip. Okay, so we're in a confined space with one another for a really long time. Okay, I have been. I've been there, yeah. It's awesome. I'd like to. Yeah. So, this one person now, potentially, because of the confined space, think about what are they saying about COVID? Is that, people that are in a confined space, for like 15 minutes or longer, that is when there's spread, right? So they're in a confined space for 15 hours with 200 people. So now this isn't true. Like, not every single person on there is going to get infected, but let's say that they do. So these 200 people are going to get off at the airport. Okay. So I'm just going to show a couple of these. Okay. But not everybody. Not everybody's going to get off that plane and get on another plane, right? But some do. And so if one infected person now gets on this plane, infects another person, so let's just say this is person 2, and this is person 3, and this is person 4, person 5. Let's say, even if it's just those 5 that got infected and got on another plane. Yep. Okay. How many people are maybe on this plane? There might be, I'm just going to keep it simple as this 200. But it could be 50, could be 10, could be 300, could be whatever. Okay? But could those people, okay, so this person's infected, they get into this 200, they go on another trip, could they start infecting other people? Could these people start infecting other people? And these people? And then these people, right? And what are those infected people going to do? Keep infecting more. They're going to get in other populations, infect them. So you see how this kind of spiders out? Okay? That's exponential growth. Okay? And that is exponential growth of a virus. One person starts it, but then now 2 people have it. And those 2 people then start infecting 3 or 4 people. And then those 3 or 4 people start infecting 6 or 7 people. Does that kind of make sense? Okay? So we can model exponential growth. So you guys remember when they were talking about this time last year, they started saying 15 days to slow the spread, or all the doctors on TV were saying they're going to flatten the curve. You guys remember that? Okay? The curve that they were talking about is the exponential curve. Okay? An exponential curve, think about what we were doing when we took that value of 2. Okay? If I take 2 and multiply it by 2, so let's just say, let's just do it this way. Okay, so these points that I'm putting on here, okay? So this is essentially 2 multiplied by itself 1 time. This is 2 multiplied by itself twice. This is 2 multiplied by itself. This should actually be a 3. Okay, 2 multiplied by itself 3 times, and 2 multiplied by itself, sorry, I messed this up. This should be a 4. 4 times. So 2 times itself, 2 times 2, 2 times 2 times 2, 2 times 2 times 2 times 2, right? Does that kind of make sense? Okay? And if I plot those points, they look like this. And if I put a curve in them, that's the curve. Okay? That is how viruses, that is how diseases spread. Okay? A lot of times it's referred to as a logistics curve. But they're going to continue to increase over and over and over. Okay? So what they wanted us to do, and we started wearing masks. We started separating from people, right? Because what their hope was that when you stop the human interactions, those spreadings stop, right? And then what happens, where did my tool go? What happens if this is increasing this way, eventually the idea is that it flattens off. And if it flattens off, then we've got it under control. Does that make sense? Okay. That is what we refer to when they were talking a month ago, flattening the curve. That's the idea, flatten this exponential curve. Okay. But that's what we're going to start investigating in this chapter. Okay. So what I'm getting at here, people always ask, when am I ever going to use this? Okay. This is maybe one of the most useful tools that we use or that impacts us in real life. Okay. Does anybody have a savings account? Okay. So when you have a savings account, what happens in a savings account? You guys know what interest is, correct? Okay. So let's say that I get, and savings accounts have very, very small interest. Okay. But I'm gonna say that I have, we call it, and we'll have an entire section about this, but I have what we call a principal. Okay. And that's the amount of money that you have invested. So let's say I put $100 in my savings account. Okay. Let's say that my interest in my savings account is 1%. Okay. APR, annual percentage rate, which means that over the duration of 1 year, that $100 is going to gain me interest of 1%. Does that make sense? So this is kind of the payoff that banks give for me to donate my money to them. For me to go put my money in their bank, they're going to give me a little bit of a return on my money. Why do they do that? Do you know why? What are banks? Are banks just like a giant locker that everybody just shoves their money in and it just sits there? Nope. Banks are businesses. Okay. So what do businesses want to do? What do we talk about earlier with the yearbook? They want to make money. Okay. So the way a bank makes money is that they give people an APR. Okay. They give you a return on keeping or stashing your money there. So when I give Chase Bank my weekly deposit and they put it in my savings account or my checking account, whatever, that money is not really there. They take it and they put the numbers in my account, but that money is really not there. They're taking that money now and they're investing it somewhere else. They're going to go buy stocks with that money. They're going to go buy mutual funds with that money. Does that kind of make sense? They're going to go buy homes with that money. A lot of banks will invest in real estate. Okay, they will, because then that money can turn into more money for them. Does that make sense? And then for them to have that capital to buy stocks, to buy mutual funds, to buy properties, they need people to put their money in their bank so they can use it, right? So the payback they give me then for me putting my money in their hands so they can use it is to give me somewhat of a return on it. Okay, now savings accounts and checking accounts, the returns on them are very small, you probably don't even notice them. Okay, but exponential equations, what they do, lost my pen. So we put our money in this bank, and they're going to give us 1% back. So after 1 year, let's just say after 1 year, I didn't touch this money, didn't do anything with it, didn't add any more to it. After 1 year, they're going to give back 1% of $100, which is $1. So now I currently own $101. Does that make sense? Okay. Now what happens is that in year 2, I get that same interest rate of 1%, but it's 1% now of $101. Okay. Well, that means then that next year I'm going to now have, after the second year, after year 2 expires, and I didn't touch this 101, I didn't add anything to it, didn't remove anything, I'm now going to get 1% of that back. So they'll give me back, okay, so 1% of this, okay, is going to be $1 and 1 penny. Does that make sense? And then that gets added to that, and in my account now I have $102.01. Does that make sense to everybody? And then year 3, the $102.01 is going to make me 1% of that. and then that gets added to the 102.101 for the fourth year. And it keeps doing it that way. Does that make sense? So if I leave that in over time, basically what we're saying is the money earned, the money that they gave you back for letting them use your money, is gaining you more money. Does that make sense? Okay. And that's defined or expressed using exponential functions, and we're gonna spend a lot of time on those types of questions because I think that's important for you guys. Okay, I think as you get out into the real world and you maybe want to buy some stocks, you want to maybe decide, what bank should I go with because they give me an APR of 3%, but maybe they only compound my money once a year, right? Or maybe they do it twice a year. What is the best as a consumer to go and put my money in? Okay. But what I'm trying to get at here, lots of places that we are going to use exponential functions. By definition, an exponential function is a function in which the variable is in the exponent. Okay. So we've seen all kinds of functions so far. We've seen linear functions. So those are functions with the greatest exponent of 1 for your variable. We've seen quadratic where it was x squared. We've seen cubic where it's x to the third. Okay? And we can keep going. We go x to the fourth, x to the fifth, that kind of thing. We've seen radical functions where the square root and the variable is underneath the square root. Now the new function is exponential, and the difference now is that the exponent is going to look something like this. The exponent is in, or the variable is in the exponent. Is that okay with everybody? Does that make sense? Okay. So that's how we're going to define and make sure that we understand that we have an exponential function. Now, it is a function, so we're going to use the function notation that we're accustomed to. But remember, we could also write it this way: y equals 2 to the x. That means the same thing. So that tells us that f of x is just a y value, right? Okay. So we've got some vocabulary that is important for us. Okay. The large number, when we write an exponential function, the large number in which that is being raised to the variable exponent, that large number is called the base. So in that example right there, we say this is the base of 2. This is a base of 3. This is a base of 10. Is that all right with everybody? Okay. What sciences are you guys in? You guys use King Henry died by drinking chocolate milk? What is that? Okay, so that's the units for the metric system, and it's deciding how to convert. So King Henry died by drinking chocolate milk. Okay, so this is your base, which is meters, grams, or liters. Okay, and now this. So if I have like 10 meters and I want to change to centimeters, I go 1, 2 spots, right? So that means I take my decimal place and I move it 2 spots. Well, that's the same thing as multiplying by 100. Okay? So what we find out is that this is 10 to the first, this is 10 squared, this is 10 to the third, 10 to the first, 10 to the second, 10 to the third, and actually these are going to be negative, and we'll talk about that later. But what happens is so what I'm trying to get at is you've experienced things in which exponential relationships exist, because there I'm either multiplying by 100, or I'm multiplying by 1,000, which is 100 times 10, or I'm multiplying by 10,000, which is 100 times 10 times 10, or it's 10 times 10 times 10 times 10. Does that make sense? Okay. So we view the metric system is essentially built using this exponential function idea. Okay. One of the important things to realize with exponential functions is how they relate to other types of functions, okay? I'm going to go with the function right here, f of x equals 2 to the x. And down here, I'm going to look at f of x, or g of x I call it, but x squared. It's the exact same components, right? It's a 2 and an x. Here, down here, it's a 2 and x. Now, they're in different spots, but look at how they differ. If I'm looking at the exponential, and I write 2 to the third, that gives me 8. 2 to the third will give me 8. Down here, okay, if I'm using x to be 3, I get 3 squared, which is 9. So 9 and 8, they're relatively close to each other, right? So at that juncture, the two functions are very similar to one another. Well, if I let 2 to the fourth, 2 to the fourth is 16, okay? Come down here and let x be 4, I get 4 squared. That is 16. They're exactly the same there, right? But the moment that I make it go to like 5, 2 to the fifth, 2 to the fifth ends up being 32. 5 squared is 25. This function is now taken over as being greater, right? Okay. If I just go out far, if I go out to 10, okay, 2 to the 10th is 1,024. Okay, 1,024. 10 squared is 100. Do you see how much faster a exponential gets large compared to a quadratic? That makes sense? Okay. If I go 2 to the 30th there, 2 to the 30th is 1 billion. Okay, 1.073 billion big. But 30 squared is only 900. Does that kind of make sense to everybody? Okay. So this exponential grows extremely fast. Whenever somebody's talking about something that increases fast, populations increase fast. Okay. Your people say that rabbits multiply like crazy, right? Start with 2 rabbits, and eventually, over a year, you might have 30 rabbits. Their growth in their population is exponential. Okay. So that's what we're talking about. That's what the relationship that's happening when we talk about exponential functions. Just look at 2 to the x. 2 to the x looks like that right there. If I compare that to x squared, x squared looks like that. Okay, now they look very similar when the x values are small. This blue line and this red line are pretty close to one another. But then they start to deviate, and this one is getting, for x values, that one is a greater, that x value right there to get to 115 for 2 to the x is an x value of a little bit bigger than 5. To get the same 115 on x squared, the x value has to be a little bit bigger than 10. Okay, so that's the relationship between exponentials and quadratics that is important to understand. You see here it says the point is that when the variable is in the exponent, even a small change in the variable can result in a very dramatic change in the value of the function or the output or the y value. Okay, small change in the x value can create a very dramatic change in the y value. Okay, every exponential function is going to be written this way. Okay, f of x equals a to the x. A being a number that is bigger than 0. Okay, and we don't want it to be 1. What is 1 raised to the x? What would that look like? Anybody have any ideas? Let's plot some points real quick. Think about 1 to the x. Okay, let's say that x is, let's say x is 0. What would be 1 to the 0? What is anything raised to the 0 power? 1. Okay. Let's say 1 to the x, but x is 1. What would be 1 to the first power be? 1. Okay. Let's say x is 2. What would be 1 to the second power? What's 1 times 1? 1. What if x is the third? What's 1 to the third power? 1 times 1 times 1? 1. What's 1 to the fourth? Okay, so what is happening? If I'm plotting all those points, What is happening here? What am I getting? I'm making a straight line. 1 to the x. I'm going to graph it. 1 to the x is that line right there. It's the line y equals 1. Okay? That is very different than anything that we're interested in. We're interested in these types of graphs, these purple ones. Okay? This orange one is completely different, right? So when we do these, we want to keep that number right there. We want to keep that bigger than 0, but we don't want to make it 1. Does that make sense? Okay. We'll stop there tomorrow. So that's an introduction of what exponential functions are, where we might use them. Tomorrow we'll actually get into calculating some stuff, some graphing, and we'll move on from there. No new homework tonight.